Assalamualaikum warahmatullahi wabarakatuh. My name is Ruzaiman bin Muzani. My matrix number is 2020479976 and I am from group RAS20348. Okay, in this video, I'm going to talk about the impact of amorphous metals on the field of soft magnetic materials. Okay, first of all, we are going to discuss about the introduction of this topic. Okay, in the beginning of amorphous metals were considered as an epoch-marking group of metallic materials. They are structurally distinct from ordinary crystalline minerals. As specific composition, they have extraordinary qualities such as high yield strength, low coercivity, and a good corrosion resistance. So far, material competition has clearly limited the spectrum of specific use of amorphous metals, but their use is still likely to increase as further developments of alloy are still progressing. Okay, next we move to the problem section of this topic. The first problem is amorphous materials are structurally distinct from ordinary crystalline materials. The second problem is the technical and economic competition among materials has clearly constrained the variety of specialized use for amorphous metals. Okay, the next we continue to the objective of this topic. The first objective is we want to know the impact of amorphous metal on the field of soft magnetic fields. The second objective is to highlight a competition among materials to obtain a new material development, innovation, or improved application. Okay, for the methodology, basic magnetic properties of amorphous metal. Okay, table 1 shows a basic structure property relation of amorphous metals. Because of the non-periodic structure of amorphous metal, hence there is no magnetocrystalline anisotropy. Since defects with strong magnetic interaction are unstable in amorphous structure, their intrinsic coercivity is small. Both of these features contribute to amorphous metals' natural soft magnetic behavior. Production of amorphous metal from the melt requires glass-forming alloy components such as the metalloids boron, silicon, carbon, and a phosphorus, or the metals titanium, zirconium, and others. Okay, for figure 1, temperature dependence of the saturation magnetization for some characteristics, crystalline and amorphous soft magnetic materials. Okay, in figure 1, for instance, the lower saturation polarization curve for a soft magnetic ferrite shows that low values of lower saturation polarization and Curie temperature do not always exclude the technological usage of material. For figure 2, composition dependence of the magnetostriction constant for some crystalline and amorphous soft magnetic materials. As illustrated in figure 2, that the magnetostriction constant may pass through zero at a certain alloy composition, but this composition may not be favorable for other properties such as a small magnetocrystalline. For figure 3, magnetization curve of an amorphous alloy in the three states of annealing in longitudinal and a transverse magnetic field and for partial crystallization. In figure 3, this represents a significant step towards achieving decreased permeability as a result of stress-induced anisotropy. Because of the decrease in specific volume of crystallized surface layer, controlled crystallization permits compressive internal stress to be created in the amorphous bar. Next, table 2, which is characteristics data to calculate eddy current losses. In table 2, it includes the effective thickness and resistivity of soft magnetic ferrites. These figures indicate that ferrites and amorphous metals are competing for low eddy current losses at high frequency. The relative magnitude of loss plays a major role in material selection for both electronic and electric power applications. Next, we move to the result. The first result of this topic is a soft magnetic materials in electronics. Lowest possible power losses are the most important criteria for the selection of magnetic core materials in electronics. Amorphous metals commonly compete with ferrites because operating frequencies are in the kilohertz range and are nearing 1 megahertz. Finally, it should be emphasized that the temperature dependency of all magnetic characteristics plays a significant role in component design, since significant differences occur between room temperature and characteristics working temperature such as 80, 100 or 120 degrees Celsius. With respect to this point, suitable amorphous material have proved to be superior to ferrites. Inductive component. Okay, in this table 4 shows the diversity of qualities required for different types and application of inductive components for 3 selected instances. The inverter transformer is made up of many components, the core of which features are a flat hysteresis loop with minimal resonance, which when combined with a high flux density, it produces the highest unipolar flux density swing. Saturable reactor cores are another example where the hysteresis loop must be very square. They are used in a variety of applications, most notably as a magnetic amplifier cores to regulate the output voltage of SMPs. To obtain a high efficiency, the remagnetizing drive current should be small. This requires a low coercivity. Apart from high hysteresis squareness, low dynamic losses of the core are clearly important in this application, which can be best addressed by thin ribbons of amorphous metal. Sensor transducer. The underlying Torr-Ducker principle is illustrated in Figure 6a. The potential lines of an applied magnetic field are displaced by a magnetoelastic interaction which can, thus, be monitored in a secondary inductive circuit. The actual concentric design which minimizes the effect of inadvertent geometric asymmetry on the magnetic signal is drawn schematically in Figure 6b. A typical output signal as a function of train is shown in Figure 6c. Whereas the original Torr-Ducker was thought to use the magnetic properties of the shaft itself, the utilization of an amorphous layer was recognized to give much higher and reliably controlled output signal. Okay, the second result is a soft magnetic materials in electrical engineering. Most electrical engineering applications require a high flux density paired with a minimal power losses at 50 or 60 Hz mains frequency or a significantly higher frequency. While in amorphous metals, the dilution by glass-forming elements decrease the average magnetic moment. Compared with classical alloys, their losses are substantially lower. This has been the primary influence of amorphous metal, notably their usage as alternate core materials in transformer distribution. Okay, for the last part, we are coming for the conclusion of this topic. The introduction of the new and better materials in this field of application is dependent not only on their immediate technical and economic advantage. Certain critical economic elements are somewhat beyond the power of the material scientist and electrical engineer. Although this work focuses on amorphous metals and their application, It also emphasized the complexities of material selection and optimization. The major goal was accomplished, which is to highlight material competitiveness as a driving force behind both new material breakthroughs and innovative or enhanced application. Okay, that's all for my explanation for this topic. Thank you for watching my video. Bye bye.